November 27, 1985. Wednesday, the day before Thanksgiving. Across the Ohio Valley and into the Great Lakes states, highways carried their heaviest load of the year. Interstate 70 through Indiana and Ohio moved traffic in both directions without pause. Interstate 75 from Michigan through Cincinnati operated at capacity. Smaller routes, US 40, US 23, State Route 2 along Lake Erie, filled with vehicles heading toward family gatherings scheduled for the following afternoon. Commercial aviation reached peak utilization. Detroit Metropolitan Airport processed departures every 3 minutes. Cleveland Hopkins handled connecting flights from both coasts. Indianapolis, Columbus, Dayton, Fort Wayne, all operated schedules compressed by demand. Rental car counters stayed open past midnight. Parking lots filled before noon. Rail freight moved on tightened schedules. Conrail operated the former Penn Central and New York Central lines through the region. Norfolk Southern ran the old Nickel Plate and Wabash routes. Thanksgiving created no pause in freight movement. Coal trains from Appalachia moved toward power plants. Intermodal containers traveled between Chicago and eastern terminals. Passenger service on Amtrak's Capital Limited and Lake Shore Limited carried full loads. This movement occurred within a narrow window. Most travelers planned arrival by Wednesday evening. Return trips would begin Friday afternoon, compressed into 48 hours. The system operated without slack. Delays compounded. Cancellations cascaded. The infrastructure supporting this movement had transitioned incompletely from autumn to winter operation. Municipal salt stockpiles remained partially depleted from the previous season. Snowplow attachments sat in storage yards. Airport de-icing equipment underwent routine maintenance. Power utilities operated with standard autumn staffing levels. Ground temperature across the region measured above freezing. Southern Ohio recorded mid-40s Fahrenheit during daylight hours. Northern Indiana and Michigan reached the upper 30s. Soil remained unfrozen. Vegetation had not fully entered dormancy. Lakes stayed ice-free. The landscape held heat accumulated through a mild early November. Weather forecasts predicted precipitation. The National Weather Service issued winter storm watches for portions of Ohio, Indiana, and Michigan. Local television meteorologists noted the possibility of snow mixing with rain. Exact timing remained uncertain. Accumulation forecasts varied. No warning suggested disruption sufficient to alter travel plans. Traffic volume peaked between 2 p.m. and 6 p.m. Wednesday. Vehicles moved slowly but continuously. Rest stops operated at capacity. Gas stations experienced lines. Fast food restaurants near interstate exits served customers without pause. The system functioned under stress but maintained flow. By early evening, temperature began dropping. Rain started in southern Ohio and central Indiana shortly after 5 p.m. Initial precipitation fell as liquid water. Pavement remained wet but passable. Visibility decreased. Traffic slowed but did not stop. The transition from rain to snow began unevenly across the region. No single moment marked the change. Southern counties along the Ohio River continued receiving rain while counties 200 miles north reported snow. The boundary shifted northward through the evening but slowly. By 9 p.m. Wednesday night, snow fell across most of Indiana and Ohio. Michigan received mixed precipitation. Illinois saw snow in eastern counties. Highways remained open. Traffic continued moving. The volume began to decrease as travelers reached destinations, but millions remained in transit. Vehicles filled every lane. Hotels near exits showed no vacancy. Service plazas maintained operations. Snow fell onto surfaces that had not yet frozen. Pavement temperature remained above 32 degrees Fahrenheit. The first flakes melted on contact. Accumulation occurred slowly, but as precipitation continued, the ground began to cool. Thermal mass diminished. Snow began to stick. The meteorological conditions producing the Thanksgiving 1985 snowstorm developed from a pattern shift that began 4 days earlier. On November 23, a strong ridge of high pressure built across western Canada and Alaska. This ridge forced the jet stream into a pronounced southward dip across the central United States. Arctic air that normally remained confined to northern latitudes spilled southward through the Great Plains. By November 25, surface temperatures across North Dakota, South Dakota, and Minnesota dropped below 0 Fahrenheit. The cold air mass moved as a coherent unit, maintaining its thermal characteristics as it progressed southeastward. Upper-level winds guided the cold air toward the Ohio Valley. No significant mountain barriers impeded its flow. Simultaneously, a low-pressure system developed over the southern plains. Gulf of Mexico moisture fed into this system, creating conditions for precipitation. The low tracked northeastward along a path that brought it directly into the advancing Arctic air. The collision zone between warm, moist air and cold, dense air established itself across the Ohio Valley and lower Great Lakes. This pattern arrived approximately 3 weeks earlier than typical winter storm tracks for the region. Historical climatology showed that significant winter storms in the Ohio Valley occurred most frequently from mid-December through February. Late November storms produced measurable snow, but rarely created sustained disruption. Infrastructure planning reflected this pattern. Municipal snow removal departments scheduled equipment deployment based on December 1 as the effective start of winter operations. Plow blades remained in storage facilities. Salt spreading equipment underwent final maintenance. Driver assignments had not yet shifted to winter schedules. The Thanksgiving storm occurred during this transition period. Temperature profiles in the atmosphere showed minimal warm layers. From the surface through the entire depth of the storm system, air temperature remained at or below freezing. This eliminated the possibility of precipitation falling as rain and then freezing on contact with the ground. Instead, snow formed in the clouds and descended as snow. No mixing zone existed. Precipitation type remained uniform. The track of the surface low pressure determined precipitation intensity. As the low moved from Missouri through Illinois and into Indiana, its counterclockwise circulation drew additional moisture northward from the Gulf. Precipitation rates increased through Wednesday evening. Snow fell steadily rather than in brief, intense bands. The duration of snowfall proved more significant than any single hourly rate. Upper-level atmospheric conditions showed minimal vertical wind shear. The jet stream remained relatively straight rather than exhibiting strong curvature. This configuration allowed the storm system to move slowly. Forward speed measured approximately 15 miles per hour. The system took more than 18 hours to cross the affected region. Prolonged snowfall accumulated to greater depths than faster-moving systems would have produced. Lake Erie contributed moisture to the northern portions of the storm. Water temperature measured in the upper 40s Fahrenheit. As Arctic air moved across the lake's surface, additional moisture evaporated into the cold air. This lake effect enhancement increased snowfall rates downwind of the lake, particularly in northeastern Ohio. Cleveland and surrounding communities received additional accumulation beyond what the primary storm system produced. Forecasting tools available in 1985 included satellite imagery, radiosonde balloon data, surface weather stations, and weather radar. Computer models existed but provided limited resolution. The National Weather Service operated the Limited Area Fine Mesh model, which updated every 12 hours. This model correctly predicted the storm's track and the occurrence of precipitation. However, it underestimated total accumulation, and the speed at which travel would become impossible. Temperature forecasts showed the challenge clearly. Models predicted temperatures in the low 30s Fahrenheit for much of the affected area. This placed conditions near the rain-snow threshold. Small variations in actual temperature determined whether precipitation fell as rain, wet snow, or dry snow. The physics of snow adhesion to pavement changed significantly across this narrow temperature range. The storm's timing relative to ground conditions created additional forecast uncertainty. Soil temperature, pavement temperature, and vegetation state all affected how quickly snow would accumulate. In mid-January, with frozen ground and cold pavement, forecasters could reliably predict that snow would accumulate at close to the rate it fell. In late November, with unfrozen soil and pavement above freezing, the initial hours of snowfall would produce little accumulation, but once thermal mass depleted, accumulation rates would increase rapidly. Weather warnings issued Tuesday and Wednesday reflected this uncertainty. Winter storm watches covered portions of Ohio, Indiana, and Michigan. These watches indicated the possibility of significant snow, but did not specify amounts or timing with precision. Winter storm warnings, which indicate higher confidence and more severe conditions, were not issued until Wednesday evening, after snow had already begun falling. The decision-making process for travelers depended on these forecasts. A winter storm watch suggested caution, but did not typically prompt cancellation of travel plans. Thanksgiving represented the year's most traveled holiday. Many people accepted some weather risk rather than miss family gatherings. The incremental nature of the forecast, progressing from possible snow to likely snow to warning conditions, occurred too slowly to affect decisions made Tuesday and Wednesday morning. Snow began falling across southern Indiana and western Ohio shortly after 8 p.m. Wednesday evening. Initial flakes melted immediately upon contact with pavement. Road surfaces remained wet. Temperature hovered at 34 degrees Fahrenheit. Traffic continued at reduced speed. Visibility decreased to less than half a mile. Windshield wipers operated continuously. As precipitation continued, the thermal exchange between falling snow and ground surfaces shifted. Each snowflake that melted extracted heat from the pavement. The cumulative effect gradually cooled the surface. Within 90 minutes, pavement temperature dropped to 32 degrees Fahrenheit. Snow began accumulating in a thin, wet layer. This transition occurred unevenly across the region. Highway sections elevated on overpasses cooled faster than at grade roadways. Cold air circulated beneath elevated structures, removing heat from both the top and bottom surfaces of the bridge deck. Snow stuck to these sections first. Drivers encountered sudden changes in traction with no visual warning in the darkness. Soil temperature remained above freezing. Ground that received direct sunlight during the day held thermal energy. Snow falling on grass, farm fields, and unpaved surfaces initially melted, but soil conducts heat slowly. The top layer cooled while subsurface temperature remained stable. After approximately 2 hours of steady snowfall, accumulation began on vegetated surfaces. The moisture content of the snow determined its behavior. Temperature near freezing produced wet, heavy flakes. Individual flakes clumped together. Snow compacted under its own weight. A 4-inch accumulation compressed to 3 inches within an hour. Water content measured approximately 15% by weight, significantly higher than the typical 10% found in colder, drier snow. This high moisture content caused immediate adhesion to vertical surfaces. Snow stuck to trees that retained leaves. Branches bent under the weight. Power lines accumulated snow along their entire length. The wet snow did not blow off in wind. Instead, it clung and compressed, creating continuous loading. Snowfall rates varied across the region but averaged between half an inch and 1 inch per hour through Wednesday night and Thursday morning. Indianapolis recorded 0.7 inches per hour between 10 p.m. Wednesday and 2 a.m. Thursday. Columbus, Ohio measured 0.6 inches per hour during the same period. Fort Wayne, Indiana reached 0.9 inches per hour. These rates persisted for 8 to 12 hours, depending on location. Total accumulation by Thursday morning varied by latitude and proximity to Lake Erie. Southern Ohio counties recorded 6 to 9 inches. Central Ohio received 8 to 12 inches. Northern Ohio, enhanced by lake effect, measured 12 to 16 inches. Indiana showed similar gradients, with southern counties receiving less than northern areas. Southeastern Michigan recorded 10 to 14 inches. The snow fell onto a landscape unprepared for accumulation. Deciduous trees had not fully dropped their leaves. The combination of remaining foliage and wet, heavy snow created structural stress. Branches designed to shed snow through their bare winter architecture instead caught and held the weight. Breakage began within hours. Urban surfaces accumulated snow differently than rural areas. Pavement retained more heat due to thermal mass of concrete and asphalt. Building heat leaked through foundations and walls, creating zones of slightly warmer temperature. Streetlights and building lights provided minimal additional warming. These factors delayed accumulation in city centers by approximately 1 hour compared to rural areas. But once accumulation began, urban snow compacted more quickly due to traffic. Parking lots presented particular difficulty. Large expanses of asphalt with minimal traffic created smooth, unbroken snow coverage. Vehicle tires compacted snow into a slick layer bonded to the pavement. Friction dropped to near zero. Lots became impassable not from depth but from surface condition. Residential streets received no treatment. Municipal snow removal prioritized highways and major arterials. Side streets accumulated undisturbed snow through the night. By Thursday morning, many residential areas had 8 to 10 inches of compacted snow. Vehicles parked at curbs became partially buried. Driveways filled. The transition from pavement to snow surface altered vehicle behavior fundamentally. Braking distance increased by a factor of 3 to 5, depending on tire condition and vehicle weight. Acceleration from a stop position required careful throttle control. Steering response became indirect and delayed. These changes occurred suddenly as vehicles moved from treated highway sections to untreated areas. Temperature during snowfall remained nearly constant. Readings held between 30 and 33 degrees Fahrenheit throughout the night. No significant warming or cooling trend developed. This stability meant snow characteristics remained uniform. No ice layer formed between snow layers. No rain mixing occurred. The accumulation consisted of wet snow from surface to top. Highway traction depends on the contact between tire rubber and pavement surface. On dry pavement, this contact occurs across approximately 100 square inches per tire. Rubber compounds grip microscopic surface irregularities. Friction coefficients measure between 0.7 and 0.9. A vehicle traveling at 60 miles per hour on dry pavement can stop in approximately 120 feet under threshold braking. Snow disrupts this contact. A layer of snow, even 1 inch thick, eliminates direct tire-to-pavement interaction. The tire instead contacts snow crystals. These crystals compress under pressure but do not provide grip. Friction coefficients drop to 0.2 to 0.4 on packed snow. Stopping distance increases to 300 feet or more. Wet snow creates additional problems. Water content reduces friction further. Tire pressure forces water from compressed snow, creating a thin liquid layer between tire and snow surface. This layer acts as a lubricant. Friction coefficients may drop below 0.2. Vehicles lose directional stability. Braking becomes ineffective. Interstate 70 through Indiana and Ohio carried continuous traffic Wednesday night. Vehicles traveled at reduced speeds but maintained movement through the initial snow accumulation. Eastbound lanes between Indianapolis and Columbus saw traffic slow from 65 miles per hour to 45 miles per hour by 10 p.m. By midnight, speeds dropped to 30 miles per hour. Traffic remained dense. Vehicles spaced at less than 100 feet separation. The first traction-related stoppages occurred on uphill grades. Interstate 70 east of Richmond, Indiana climbs a gradual slope over several miles. Trucks in the right lane slowed as drive wheels lost grip. Several trucks stopped completely on the grade. Following traffic slowed, then stopped. Within 15 minutes, the right lane became blocked. Traffic merged left. Flow rate decreased. Similar patterns developed on Interstate 75 through Ohio and Michigan, Interstate 80 through northern Indiana and Ohio, and Interstate 69 through Indiana and Michigan. Each highway included grades that, while modest in dry conditions, became impassable under snow. Trucks carrying loaded trailers could not maintain momentum. Once stopped, they could not restart on the incline. Passenger vehicles experienced loss of control incidents. Most occurred during lane changes or when braking. A vehicle moving at 30 miles per hour on packed snow requires careful steering input. Abrupt movements cause the vehicle to continue in its original direction despite wheel angle change. Drivers unaccustomed to this behavior overcorrected. Vehicles rotated and blocked lanes. By 2 a.m. Thursday, multiple sections of every major highway through the region experienced stopped traffic. Vehicles sat stationary in all lanes. The gaps between vehicles closed as following traffic approached and stopped. Eventually, highways held lines of vehicles extending for miles, unable to move forward or backward. Snow continued falling. Accumulation on stopped vehicles reached 4 inches by 4 a.m., 6 inches by 6 a.m. Drivers ran engines periodically to maintain heat. Fuel gauges dropped. Some vehicles ran out of fuel and could no longer provide heat. Visibility remained below 1/4 mile. Headlights illuminated falling snow but provided little distance perception. Drivers could not see the length of the traffic queue ahead. Many assumed temporary stoppage and waited. No information system existed to communicate the extent of the blockage. State police in Ohio, Indiana, and Michigan received accident reports continuously through the night. Each accident required response. Police vehicles could not reach accident scenes. Tow trucks dispatched to clear disabled vehicles became stuck in the same traffic. The incidents accumulated without resolution. Highway design included emergency turnarounds at intervals, intended for official vehicles. Snow covered these access points. Markers disappeared under accumulation. Even if identified, the turnarounds led to parallel lanes equally blocked. No escape routes existed. Some drivers attempted to reverse and exit via the most recent entrance ramp. This required coordinating movement of dozens of vehicles. In darkness, with falling snow and no communication, such coordination proved impossible. Vehicles attempting to reverse collided with vehicles behind them. The situation worsened. Salt trucks operated on major routes but encountered the same traffic. Plow trucks could not push through stopped vehicle lines. In some cases, snowplows operated in the left lane while traffic sat stopped in the right lanes. But the plows reached the traffic queue and could proceed no further. They sat, waiting with all other vehicles. Road surface temperature continued to drop. By early Thursday morning, pavement measured 28 to 30 degrees Fahrenheit. Snow bonded directly to the surface. The base layer became ice-like in hardness. Subsequent snow layered atop this foundation. Total depth reached 8 inches on highway lanes, more in areas where plows had not operated. Chains would have provided improved traction, but few vehicles in the region carried chains. November travel did not typically require winter equipment. Tire shops had not yet stocked winter tires. Most vehicles operated on all-season radials designed for mixed conditions but not deep snow. Exit ramps became impassable. The ramps typically included curves and grades. Snow accumulation combined with reduced traffic created uncompacted surfaces. Vehicles attempting to exit highways became stuck on ramps. This blocked the ramp for all following traffic. Vehicles could neither exit nor return to the highway. By dawn Thursday, traffic on all major highways through the Ohio Valley and lower Great Lakes region remained stopped. No movement occurred. Tens of thousands of vehicles sat in place. Fuel ran low. Heat became intermittent. Daylight revealed the extent of the blockage but provided no solution. Interstate highways provide no shelter. Vehicles stopped on a highway occupy positions designed for continuous movement, not stationary occupancy. No buildings stand within reach. No services exist beyond the roadway. Safety depends on mobility. When mobility ceases, vehicles become isolation chambers. By Thursday morning, November 28, Thanksgiving Day, Hundreds of miles of highway held stopped traffic. Interstate 70 from Indianapolis to Columbus remained blocked. Interstate 75 from Cincinnati through Dayton to Toledo showed no movement. Interstate 80 across northern Ohio and Indiana held continuous lines of vehicles. Each highway segment contained thousands of people unable to reach destinations or return to origins. Fuel became the immediate concern. Vehicles stopped Wednesday evening had been in operation for hours before the stoppage. Many began Thursday morning with half tanks or less. Engines cycled on and off to provide heat. A typical passenger car consumed approximately 1 gallon of gasoline per hour while idling. Trucks used more. A vehicle with 8 gallons remaining at dawn could maintain heat for 8 hours, until mid-afternoon. Temperature Thursday morning measured in the low 20s Fahrenheit. Wind speed reached 15 miles per hour. The combination created wind chill values near 10 degrees Fahrenheit. Vehicles with heat maintained interior temperatures in the 60s. Vehicles without heat dropped to exterior temperature within 30 minutes. Some occupants wore clothing appropriate for indoor Thanksgiving gatherings, not extended outdoor exposure. Dress shoes, light jackets, no gloves, no hats. Preparation for weather assumed building-to-vehicle-to-building transitions, not sustained highway occupancy. Snow accumulation on vehicles reached 10 inches by mid-morning Thursday. Exhaust pipes on low-clearance vehicles became partially blocked. Carbon monoxide entered some vehicles. Occupants needed to periodically exit and clear exhaust areas. This required stepping into 10 inches of snow in inadequate footwear. Communication infrastructure in 1985 offered limited options. Some vehicles contained CB radios, used primarily by truck drivers. Cellular phones existed but remained rare and non-functional in rural areas. No text messaging existed. No navigation systems provided traffic information. Drivers could not call for assistance, could not inform family of their location, could not determine the extent of the blockage ahead. Battery-powered AM/FM radios provided the only information source. Local radio stations reported the storm and road closures, but offered little specific guidance for those already stranded. Broadcasts confirmed what occupants observed. Roads remained closed. Travel was impossible. No estimate for reopening appeared in reports. Highway patrol officers worked to reach stranded vehicles but encountered the same impassable conditions. In some sections, officers walked along highways, checking vehicles, identifying medical emergencies. Walking progress measured approximately 1 mile per hour through the snow. An officer could reach perhaps 20 vehicles per hour. Thousands required checking. Emergency services received calls from motorists reporting medical issues, fuel exhaustion, vehicles without heat. Ambulances could not reach patients. Fire departments could not access vehicles with carbon monoxide exposure. The response infrastructure depended on road access. No alternative existed. Some sections of highway passed through rural areas with scattered farmhouses visible from the road. A few occupants abandoned vehicles and walked toward these structures. Distances that appeared short from a moving vehicle required 30 minutes or more to traverse through snow. Some farmers opened homes to stranded travelers, providing heat and food. But capacity remained limited. A farmhouse could shelter perhaps a dozen people. Hundreds remained in vehicles nearby. Rest areas became concentration points. Vehicles that reached rest areas before becoming fully stopped found limited shelter. Rest area buildings provided heat, restrooms, and vending machines, but capacity designed for peak load of perhaps 50 people now held 200. Buildings filled. Vehicles parked in every available space and across areas not designated for parking. Snow removal at rest areas occurred unevenly. Some facilities had equipment and staff present. Others operated with minimal staffing on the holiday. Parking lots accumulated snow without clearing. Vehicles entering rest areas became stuck in unplowed snow and could not reach buildings. Truck drivers, accustomed to overnight stops in vehicles, possessed better preparation. Sleeper cabs provided insulated spaces. Diesel fuel capacity supported longer idling. Food and water supplies existed in many trucks. Truckers used CB radios to share information, coordinate assistance, and maintain communication chains. This created information networks unavailable to passenger vehicle occupants. Highway bridges presented particular danger. Wind speed increased across bridges due to reduced wind resistance. Bridge deck temperatures dropped faster than at grade roadway sections. Ice formed on bridge surfaces. Vehicles on bridges experienced both colder temperatures and higher wind exposure. Some bridges on Interstate 70 and Interstate 75 held stop traffic for the entire day Thursday. Elderly occupants and very young children represented the most vulnerable population. Elderly individuals tolerated cold less effectively and faced increased risk from prolonged sitting. Infants required temperature-controlled environments. Vehicles containing these vulnerable individuals became priority concerns for emergency services, but reaching them proved impossible in most cases. Some vehicles ran out of fuel by mid-morning Thursday. Occupants faced a decision: remain in a vehicle without heat or attempt to walk to uncertain shelter. Walking in 10 inches of snow, in temperatures near 20 degrees for unknown distances, carried significant risk. But remaining in an unheated vehicle carried equal or greater risk. Most chose to stay. Daylight provided visibility but no solutions. Occupants could see the line of vehicles extending in both directions. They could see snow continuing to fall. They could see plows unable to advance. The visual confirmation of the situation's extent offered no comfort. Railroad switches consist of movable track sections that guide trains from one track to another. These switches operate through mechanical linkages or electric motors that shift the rail position. In freezing conditions, moisture enters the switch mechanism. Snow and ice prevent movement. A single frozen switch blocks entire rail lines. Conrail operated the primary freight network through the Ohio Valley. Main lines connected Chicago to eastern terminals through northern Indiana, northern Ohio, and western Pennsylvania. Secondary lines served Cleveland, Columbus, Cincinnati, and Detroit. Thanksgiving week carried standard freight volume. Trains operated on schedules that assumed unimpeded movement. Snow began affecting rail operations Wednesday evening. Switch heaters, installed at critical junctions, operated continuously. But these heaters addressed ice formation, not snow accumulation. Wet, heavy snow packed around switches faster than heaters could melt it. Yard workers manually cleared switches, but snowfall rates exceeded clearing capacity. The first delays occurred at classification yards where trains are assembled. Conrail's yard in Elkhart, Indiana processed trains moving between Chicago and eastern destinations. Thursday morning, switch clearing at Elkhart fell behind schedule. Trains entering the yard stopped and waited. Following trains stopped on main lines approaching the yard. Within hours, the main line held a queue of trains unable to proceed. Similar delays developed at yards in Toledo, Cleveland, and Indianapolis. Each yard represented a bottleneck in the system. Trains could not bypass yards. Freight must be sorted and reassembled according to destination. The accumulating delays propagated through the network. On main lines between yards, locomotives maintained better progress than highway vehicles. Steel wheels on steel rails provided superior traction compared to rubber tires on snow. Trains continued operating through conditions that stopped trucks, but speed dropped. A main line designed for 50-mile-per-hour freight service operated at 20 to 30 miles per hour. Scheduled delays accumulated. Signal systems experienced interference. Railroad signals depend on electrical circuits through the rails. Snow and ice disrupted these circuits. Signal systems defaulted to red, stop, when circuit integrity became uncertain. Train crews encountered red signals with no apparent cause. They stopped, waited, then proceeded under restricted speed rules. These stops added further delays. Passenger rail service on Amtrak's Capital Limited and Lake Shore Limited routes continued with delays. The Capital Limited operated daily from Washington, D.C. through Pittsburgh and across Ohio to Chicago. Thanksgiving week carried full passenger loads. The train departing Washington Wednesday evening encountered snow through West Virginia and Ohio. Speed restrictions and switch delays added hours to the schedule. A train scheduled to reach Chicago Thursday afternoon arrived Friday morning. Air transportation failed more completely than rail. Airports require clear pavement on runways, taxiways, and aprons. Aircraft require de-icing before departure. Ground support equipment must move freely. These requirements became impossible to meet under sustained snowfall. Detroit Metropolitan Airport handled 400 scheduled flights on an average November day. Thanksgiving week increased this to 500 flights. Wednesday evening operations continued as snow began. Aircraft received de-icing treatment. Runways underwent continuous plowing. Departure delays increased, but flights continued. By midnight Wednesday, snowfall rate exceeded the capacity of de-icing operations. Each aircraft required 15 to 20 minutes of de-icing. By the time treatment finished, new snow accumulated on the aircraft. Repeat treatments began. Fuel loaded for flights diminished as aircraft idled awaiting clearance. Some flights canceled due to fuel limitations. Runway snow removal operated around aircraft movements. Snowplows cleared runways between takeoffs and landings. This process worked adequately when snowfall measured half an inch per hour. At snowfall rates approaching 1 inch per hour, the runway required continuous plowing. But continuous plowing prevented aircraft operations. The airport faced an impossible choice: clear runways or move aircraft. It could not do both simultaneously. Cleveland Hopkins Airport closed Thursday morning. Accumulation exceeded 12 inches. Plows could not maintain clear runways. All departures canceled. Arriving flights diverted to alternate airports. Passengers in the terminal could not leave. Roads to the airport remained closed. The terminal held thousands of people intended for connecting flights or pickup by family. Indianapolis, Columbus, Fort Wayne, Dayton, Toledo, all airports in the affected region reduced operations or closed entirely Thursday. Aircraft scheduled to arrive became stranded at origin airports. Aircraft already airborne diverted to airports outside the storm area. The entire regional aviation network ceased functioning. Passengers already inside airport terminals faced extended delays with limited food service. Thanksgiving Day left most airport restaurants closed or operating with minimal staff. Vending machines sold out. Terminal buildings provided heat and shelter but not accommodation. People slept on floors and benches. Aircraft de-icing fluid supply became critical. Airports stocked fluid based on typical winter usage. The early season storm depleted supplies. Reordering required delivery by truck. Trucks could not reach airports. Even if runways could be cleared, aircraft could not be de-iced. Air traffic control continued operations but managed virtually no traffic. Controllers monitored empty radar screens. Flight plans filed for Thursday operations canceled systematically. The airspace remained open but unused. Ground support equipment, baggage tractors, fuel trucks, catering vehicles became stuck in snow around airport aprons. Aircraft at gates could not be serviced. Pushback tractors could not move aircraft. Jetways froze in position. Gates became unusable even if flights could operate. By Thursday afternoon, the integrated transportation system serving the Ohio Valley and lower Great Lakes had ceased functioning. Highways held stopped traffic. Rail operations ran hours behind schedule. Air transportation had halted. No alternative remained. Movement stopped. Electrical power generation in the Ohio Valley relied on a mixture of coal-fired plants, nuclear units, and natural gas facilities. Ohio operated 7 coal plants with total capacity exceeding 6,000 megawatts. Indiana's coal plants generated approximately 8,000 megawatts. Michigan operated both coal and nuclear facilities. These plants supplied power to a grid serving approximately 20 million people. Thanksgiving Day typically showed reduced electrical demand. Commercial and industrial facilities operated at minimal capacity. Offices closed for the holiday. Manufacturing plants shut down or ran reduced shifts. Residential demand remained steady: heating, lighting, cooking. The overall load measured approximately 15% below typical weekday demand. The November 1985 storm reversed this pattern. Temperature dropped to the low 20s Fahrenheit by Thursday morning. Heating systems activated continuously. Residential demand increased. Simultaneously, commercial buildings, though unoccupied, required heating to prevent pipe freezing. Industrial facilities maintained base heating to protect equipment. Demand exceeded typical winter levels. Electric heating systems drew maximum power. Resistance heaters operated at full capacity. Heat pumps in supplemental heating mode increased load. A typical household using electric heat consumed 3 to 5 kilowatts continuously. Across millions of homes, this created gigawatts of additional demand. Natural gas heating, while not affecting electrical load directly, created demand surges in gas distribution systems. Furnaces activated simultaneously as temperature dropped. Natural gas pressure in distribution lines decreased. System operators increased flow from transmission pipelines to maintain pressure, but transmission capacity had limits. The storm disrupted fuel supply logistics. Coal deliveries to power plants traveled by rail and truck. Both transportation modes experienced delays. Plants maintained coal stockpiles designed for several days' operation. Thursday consumption drew down these stockpiles. New deliveries failed to arrive. Reserve margins decreased. Rail deliveries represented the primary coal supply method. Unit trains, dedicated coal trains running between mines and power plants, operated on fixed schedules. These trains traveled from Appalachian coal fields through the affected storm region. Switch delays and main line blockages prevented on-time delivery. A power plant expecting a coal delivery Thursday morning might not receive it until Friday. Nuclear plants operated independently of weather-related fuel supply issues. However, nuclear plants required continuous cooling water circulation. Water intake structures, typically drawing from rivers or lakes, experienced ice formation. Phasal ice, small ice crystals suspended in water, clogged intake screens. Plant operators managed these conditions but could not ignore them. Power transmission lines accumulated snow and ice. High-voltage lines, suspended between towers, hung in free air exposed to wind and precipitation. Wet snow adhered to conductor cables. Weight increased. Cables sagged lower. In extreme cases, cables contacted vegetation or dropped below minimum ground clearance. Wind caused ice-loaded cables to sway, sometimes contacting each other and causing short circuits. The storm's wet snow created particularly heavy line loading. A conductor cable might accumulate 1 inch of ice radially around its circumference. The additional weight per mile of cable reached thousands of pounds. Tower structures designed for this loading generally held, but distribution lines on wooden poles experienced failures. Poles broke. Lines dropped. Distribution system failures began Thursday morning in rural areas. Tree branches, loaded with wet snow, broke and fell onto power lines. A single branch could de-energize a distribution circuit serving hundreds of homes. Utility crews dispatched to repair these faults encountered impassable roads. Bucket trucks became stuck in snow. Crews could not reach outage locations. Urban areas experienced fewer tree-related outages but faced overload conditions. Substations distributed power through transformer banks rated for specific maximum loads. The increased heating demand pushed transformers to rated capacity. Some older transformers, already operating near capacity under normal winter conditions, experienced overload shutdown. Automatic protective systems disconnected circuits. Outages occurred despite intact lines. Utility control centers monitored system load in real time. Operators watched demand climb Thursday morning. Reserve capacity decreased. The margin between available generation and total demand narrowed. If demand exceeded supply, automatic load shedding systems would activate, creating controlled rolling blackouts to prevent total system collapse. Power plant operators increased output to maximum capacity. Coal plants ran at peak load. Nuclear units maintained maximum safe output. Natural gas plants activated. But total available generation had limits. Some plants could not deliver rated capacity due to reduced coal stockpiles or maintenance status. The system operated with minimal reserve. Natural gas distribution pressure dropped in some areas. Residential furnaces burned gas continuously. Commercial and industrial gas loads remained active. The distribution system, designed for average winter day loads, experienced peak demand. System operators reduced pressure slightly across the network to maintain supply. Some furnaces, particularly older units, experienced ignition difficulties at reduced pressure. Propane users in rural areas faced separate concerns. Propane tanks at residences held limited supply. A typical home tank supplied 1 to 2 weeks of heat under normal winter conditions. At sustained sub-freezing temperatures with continuous furnace operation, tank supply lasted less than 1 week. Propane delivery trucks could not travel to refill tanks. Rural residents monitored tank gauges and reduced heating to extend supply. Electricity outages eliminated heating for all electric homes. A home with electric resistance heat or heat pump, once power failed, had no backup system. Interior temperature dropped toward exterior temperature. Occupants required alternative heat sources. Fireplaces and wood stoves, where present, provided some heat. Homes without these features became uninhabitable within hours. By Thursday afternoon, scattered power outages affected tens of thousands of customers across Ohio, Indiana, and Michigan. Each outage represented not only loss of heat, but loss of lighting, refrigeration, and communication. Corded telephones, common in 1985, required line power in many installations. Battery-powered portable phones offered backup, but batteries depleted within hours. The electrical grid, designed for reliability and redundancy, operated Thursday under stress conditions. Operators maintained system stability through careful load management. But the combination of increased demand, reduced fuel supply, transmission line damage, and distribution system failures created conditions approaching system limits. The infrastructure functioned but with no margin for additional disruption. Columbus, Ohio, population approximately 565,000, occupied the geographic center of the state. Interstate 70 ran east-west through the city. Interstate 71 ran north-south. State Route 315 and other limited-access highways provided intracity movement. The street grid included hundreds of miles of city streets. All served as arteries of movement supporting the city's function. Thursday morning, all routes into Columbus remained impassable. Interstate 70 held stop traffic in both directions east and west of the city. Interstate 71, north toward Cleveland, showed no movement. Interstate 71, south toward Cincinnati, remained blocked. Vehicles attempting to reach Columbus by alternative state routes encountered similar conditions. The city became isolated not by distance, but by the impossibility of travel. Columbus maintained snow removal equipment and staff. Snowplows deployed Wednesday evening. Primary streets received continuous treatment. Major arterials remained passable for local traffic, but connecting to the outside required interstate highways. City equipment operated on city streets. State Highway Department equipment operated on interstates. The jurisdictional boundary created a functional barrier. Within Columbus, city services operated. Electric power remained available to most areas. Natural gas supplied heating. Water and sewer systems functioned. Grocery stores opened, though many staff members could not reach work. The city operated internally but existed in isolation. Similar patterns occurred throughout the region. Indianapolis, population approximately 710,000, faced identical isolation. Dayton, Fort Wayne, South Bend, Toledo, all remained internally functional but externally cut off. The isolation resulted not from infrastructure failure within cities, but from the impossibility of movement between cities. Cincinnati sat along the Ohio River in the southwestern corner of Ohio. Interstate 75 connected Cincinnati north to Dayton and Detroit. Interstate 71 connected Cincinnati northeast to Columbus and Cleveland. The city served as a regional hub. Thursday, it served nothing beyond its own boundaries. Interstate approaches to the city held stop traffic. The airport closed. Rail traffic delayed. No movement occurred in or out. Cleveland, along Lake Erie's southern shore, received enhanced snowfall from lake effect. Total accumulation Thursday morning reached 16 inches in eastern suburbs. The city's snow removal capacity exceeded most cities in the region due to routine lake effect snow experience. Crews operated continuously. Major streets remained passable. But Cleveland faced the same external isolation. Highways out remained blocked. The airport closed. Regional connectivity vanished. Detroit, the region's largest city at approximately 1.1 million population, operated automotive industry facilities that employed hundreds of thousands. Thanksgiving week traditionally meant reduced production. Many plants closed for the 4-day holiday. Workers planned to return Friday. The storm made return impossible. Even if plants opened, workers could not reach them. Production delays began. Smaller cities experienced more severe internal disruption. Akron, Ohio, population approximately 235,000, received 15 inches of snow by Thursday afternoon. The city's snow removal equipment, adequate for typical winter storms, could not clear streets at the rate snow fell. Secondary streets remained unplowed. Residential areas became inaccessible. Emergency vehicles could not reach all addresses. Fort Wayne, Indiana, population approximately 170,000, faced similar internal challenges. The city operated 30 snowplows. Under normal winter snow, these proved sufficient. Thursday, they remained insufficient. Plow operators worked continuous shifts. Equipment broke down from overuse. Replacement parts required ordering from suppliers in other cities. Delivery became impossible. The timing of the storm on Thanksgiving Day eliminated commercial solutions. Equipment rental companies closed for the holiday. Towing services operated with minimal staff. Auto repair shops closed. The normal support infrastructure that mitigated storm impacts remained unavailable. Cities requested assistance from the National Guard. Ohio's governor activated Guard units Thursday morning. Guard members reported to armories. But Guard vehicles, trucks, personnel carriers, remained at armories in other cities. Moving this equipment to where it was needed required travel through the same impassable roads. Guard units could assist within their own cities but could not deploy regionally. Intercity commerce stopped. Trucking companies operated terminals in each major city. Trucks scheduled for delivery Thursday sat at terminals. No deliveries occurred. Warehouses expected deliveries that did not arrive. Retail stores began Thursday with inventory on hand. No restocking occurred. Perishable goods in transit spoiled. The regional economy operated as an integrated system. Auto parts manufactured in one city supplied assembly plants in another city. Just-in-time inventory practices meant parts arrived as needed, not weeks in advance. The storm stopped this flow. Assembly plants, even if they opened Friday, lacked parts. Production could not resume immediately even after roads cleared. Medical supply distribution followed similar patterns. Hospitals maintained limited on-site supply of most items. Regular deliveries refreshed stocks. The storm prevented deliveries. Hospitals began drawing down supplies. Most had sufficient inventory for several days, but specialized items existed in limited quantity. Medications, blood products, surgical supplies, all had finite inventory and no resupply. The geographic scale of the affected region prevented assistance from outside areas. If Columbus faced an isolated emergency, Cleveland, Cincinnati, or Indianapolis could send equipment and personnel. When all cities faced simultaneous disruption, no external assistance existed. Chicago, to the west, experienced less severe storm effects and might have sent aid, but distance prevented rapid deployment. Eastern cities, beyond the storm's reach, lay too far away to help. Cities function through networks that extend beyond municipal boundaries. Power generation, food distribution, fuel supply, medical resources, emergency equipment all depend on regional and national systems. The storm did not destroy these systems, it temporarily disconnected them. Each city became an island, operating on internal resources with no external support. By Thursday evening, the isolation continued. Roads remained closed. No traffic moved. Cities operated autonomously. The regional network that normally integrated economic and social activity lay dormant. Reestablishing this network required first clearing the roads. That clearing could not begin until the storm ended, and until equipment could actually reach the roads to clear them. Snow removal requires access. Plows must reach the snow. Trucks must collect and transport it. Crews must operate equipment continuously. When snow covers empty roads, clearing proceeds systematically. When snow covers roads filled with stopped vehicles, clearing becomes impossible. Ohio maintained approximately 800 snowplows statewide. These plows served 2,500 miles of interstate highway, 6,000 miles of U.S. routes, and 20,000 miles of state routes. Under typical winter conditions, this equipment cleared major routes within hours of storm passage. Thursday morning, November 28, nearly every plow remained blocked by stopped traffic. Snowplow operators reached their assigned vehicles. They started engines, engaged plow blades, activated salt spreaders. They moved forward until reaching stopped vehicles. Then they stopped. The plow could not push through a line of occupied cars. The operator waited. Traffic did not move. The plow sat idle. Some highway sections had emergency access points where plows could enter. Operators used these access points, plowed until reaching stopped traffic, then reversed and plowed the cleared section again. This created short stretches of clear pavement surrounded by miles of impassable highway. The cleared sections provided no practical benefit. Tow trucks represented the theoretical solution. Move the stopped vehicles off the highway, allowing plows to clear the lanes. But tow trucks faced three obstacles. First, they could not reach the stopped vehicles. Access roads leading to highways remained snow-covered. Second, even if a tow truck reached a stopped vehicle, where would it tow the vehicle? Every exit ramp, every side road also held snow. Third, the sheer number of stopped vehicles exceeded available tow trucks by orders of magnitude. Ohio operated perhaps 500 tow trucks statewide. Thousands of vehicles sat stopped. Some vehicles had simply run out of fuel. These became stationary obstacles. Other vehicles experienced mechanical failure from extended idling or from stress of snow operation. Frozen fuel lines, dead batteries, overheated engines, failures accumulated. Each failure added a vehicle that could not move under its own power. Highway patrol officers worked to identify vehicles that could potentially move. Officers walked from vehicle to vehicle, determining which had fuel, which had operational heating, which contained occupants needing immediate assistance. This information gathering took hours. Radio communication relayed findings to command centers, but even identifying which vehicles could move did not solve the problem of where they could move to. The optimal clearing strategy required all vehicles to exit the highway onto side roads, even snow-covered side roads. This would clear the highway for plows. But coordinating this evacuation required communication with every driver. No system existed for this communication. Drivers heard radio broadcasts telling them to stay in vehicles and wait. Contradictory instructions created confusion. Some sections of highway saw attempted self-organized clearing. Drivers exited vehicles and walked forward, communicating with other drivers. They developed plans to move vehicles onto shoulders, allowing one lane to clear. These plans worked in isolated instances across a few hundred feet. But they required continuous coordination, physical effort to push stuck vehicles, and willingness of all participants to cooperate. Most sections lacked this coordination. Military assistance could have provided organizational capacity and equipment. The National Guard, if deployed in sufficient numbers with appropriate vehicles, could have systematically cleared highways. But Guard deployment required mobilization time. Units needed to assemble, equip, and travel to affected areas. Travel required passable roads. The circular dependency, need clear roads to bring clearing equipment, had no immediate solution. Thursday afternoon brought another complication. Temperature dropped further. Snow that had been wet and heavy Thursday morning began freezing into solid mass. Vehicles that might have been pushed or towed Thursday morning became frozen in place by Thursday afternoon. Ice bonded tires to pavement. Snow packed around wheel wells froze solid. Vehicles became fixed obstacles. Fuel trucks could not reach stopped vehicles to provide fuel. Even if a fuel truck reached a highway, transferring fuel from truck to individual vehicles, one by one, would require hours per truck. The logistics of refueling thousands of vehicles in place proved impossible. Emergency services prioritized medical evacuations. Ambulances could not reach patients, but in some cases, emergency medical technicians walked to vehicles carrying medical equipment. They treated patients in place or, in critical cases, helped patients walk to ambulances staged on access roads. Each evacuation took hours. Only the most critical cases received this treatment. Helicopters provided some evacuation capacity. Medical helicopters transported critical patients from highway scenes to hospitals. But helicopters required clear landing zones. Highways filled with vehicles provided no landing space. Helicopters landed in adjacent fields when possible, requiring patients to be carried across snow-covered ground. Helicopter operations continued through Thursday, but handled only a small fraction of those needing assistance. By Thursday evening, snow had largely stopped falling. Total accumulation varied by location, but averaged 12 to 14 inches across the affected region. Clearing this accumulation from thousands of miles of highway represented days of work under ideal conditions. With highways occupied by stopped vehicles, no clearing occurred. The first section to clear was Interstate 70 west of Indianapolis. Snow tapered earlier in western Indiana. Stopped traffic in this section involved fewer vehicles. By Thursday evening, some vehicles had enough fuel to restart movement. A few vehicles moved, creating gaps. Plows entered these gaps. Slowly, over hours, traffic began moving at walking speed. By midnight Thursday, westbound Interstate 70 west of Indianapolis showed movement. Speeds remained below 10 miles per hour. But movement occurred. Other sections remained stopped. Interstate 75 through Ohio, Interstate 80 across northern Indiana and Ohio, Interstate 69 in Michigan, all held stopped traffic into Friday morning. Occupants spent more than 24 hours in vehicles. Fuel exhausted. Heat failed. Cold penetrated. Some occupants abandoned vehicles Friday morning. They walked toward visible buildings or followed exit signs hoping to find shelter. Walking through 14 inches of snow required substantial effort. Many walked a quarter mile before reaching any structure. Some walked longer distances. A few became disoriented or exhausted and required rescue themselves. The clearance of highways ultimately required the storm to end, temperatures to rise slightly, and a slow, organic process of vehicle movement. No systematic clearing operation proved possible. Instead, over Friday and into Saturday, vehicles incrementally began moving. Plows worked behind traffic, clearing what they could. The process took days. Friday, November 29. Temperature climbed to 34 degrees Fahrenheit by mid-morning. Sunlight, though filtered through clouds, provided radiative heating. Snow compacted under its own weight. The top layer began melting slightly. Surface conditions remained difficult, but the peak challenge had passed. Traffic on Interstate 70 west of Indianapolis continued moving slowly Friday morning. Vehicles that had been stopped since Wednesday night traveled at 5 to 15 miles per hour. Plows followed, clearing lanes after vehicles passed. By noon Friday, westbound traffic moved continuously, though slowly. Eastbound lanes remained more difficult. The grade climbing toward Indianapolis held heavier traffic density. Interstate 75 through Ohio began clearing Friday afternoon. Traffic in Dayton, which had been stopped for over 30 hours, started moving. Vehicles traveled in single file in the left lane while plows cleared the right lanes. The process resembled a convoy more than normal highway traffic. Speeds rarely exceeded 20 miles per hour, but movement occurred. Vehicles that had exhausted fuel remained stationary. Tow trucks, now able to access some highway sections, began removing disabled vehicles. Priority went to vehicles blocking lanes. A single disabled vehicle in a travel lane created bottlenecks that slowed entire highway segments. Tow trucks worked systematically, moving vehicles to shoulders or to the nearest exit ramp. This work continued through Friday and into Saturday. Abandoned vehicles created complications. Some occupants, after leaving vehicles Thursday or Friday, did not return. Vehicles sat empty, locked, with keys inside. Tow operators could not easily distinguish abandoned vehicles from those whose occupants had temporarily left to seek shelter. Police marked vehicles that appeared abandoned, but confirming abandonment took time. Some vehicles remained on highways for days. Highway Patrol estimated that across Ohio, Indiana, and Michigan, approximately 1,500 vehicles were abandoned or disabled during the storm. These vehicles required towing, storage, and eventual owner contact. The process extended through the following week. Fatalities occurred. Exact numbers varied by state, but across the region, approximately 50 deaths attributed directly to the storm. Causes included carbon monoxide poisoning from vehicle exhaust in snow-blocked conditions, hypothermia from exposure after leaving vehicles, heart attacks from physical exertion, and vehicle accidents during the initial hours of snowfall. Additional deaths occurred indirectly. Medical emergencies that could not receive timely treatment, elderly individuals without heat, pre-existing conditions exacerbated by cold exposure. Hospitals in major cities received patients Friday and Saturday as roads became passable. Emergency departments saw cases of frostbite, hypothermia, exhaustion, and complications from extended cold exposure. Most cases resolved with treatment, but some required extended hospitalization. Property damage primarily involved vehicles. Engines damaged from extended idling, frozen fuel systems, depleted batteries, body damage from snow load, interior damage from occupant survival efforts. These issues affected thousands of vehicles. Insurance claims began arriving Monday, December 2. Processing these claims required months. Airport operations resumed Saturday morning, November 30. Runways had been cleared Friday, but aircraft and crew positioning required additional time. Many aircraft scheduled for Columbus sat in cities outside the storm region. These aircraft needed to return before normal flight schedules could resume. Crews had exceeded duty time limits and required rest periods. The air transportation network required 2 days to return to normal operations. Rail operations normalized more quickly. Freight trains resumed movement Friday, though with delays from backlog. Yards cleared accumulated trains through the weekend. By Monday, December 2, freight service operated near normal schedules. Passenger rail returned to schedule by Saturday. Power outages cleared gradually. Utility crews, able to access damaged sites by Friday, began repairs. Tree limbs on lines required removal. Broken poles needed replacement. Some repairs required specialized equipment and parts. Rural areas, served by long distribution lines through wooded areas, experienced the longest outage durations. Some rural customers remained without power until Sunday, December 1. Natural gas and propane supply normalized more slowly. The backlog of delivery demand exceeded available trucks. Propane suppliers prioritized customers with lowest tank levels. Some rural residents received deliveries as late as Tuesday, December 3. Natural gas distribution system pressure returned to normal levels by Saturday as demand decreased with rising temperatures. Cities cleared streets through the weekend. Residential areas, last priority after highways and major streets, saw plows Saturday and Sunday. Some side streets remained snow-covered into the following week. Parking lots, private property responsibility, cleared according to individual property owner capability. Many commercial lots remained partially snow-covered for days. Economic activity resumed unevenly. Retail stores opened Saturday for post-Thanksgiving shopping, but customer traffic remained far below normal. Many potential shoppers faced impassable home streets or lacked functioning vehicles. Stores experienced inventory shortages from missed deliveries. The disruption to the busiest shopping weekend of the year affected retail revenue through December. Manufacturing facilities reopened Monday, December 2, but operated below capacity. Parts shortages from disrupted supply chains limited production. Workers who lived in areas with still impassable streets could not report. Some facilities operated at 60 to 70% capacity through the first week of December. Auto assembly plants, particularly those in Detroit, faced extended parts shortages. Just-in-time inventory meant no buffer stock existed. A missed parts delivery stopped assembly lines. Some plants shut down completely Monday and Tuesday, reopening only after supply chains reestablished. The lost production affected quarterly output figures. Schools, scheduled to reopen Monday after Thanksgiving break, remained closed in many districts. School bus routes required passable roads. Rural routes remained snow-covered. Urban schools opened on varied schedules. Some districts opened Monday, others delayed until Tuesday or Wednesday. College students returning to campuses faced travel difficulties. Some universities extended break by several days. Postal service experienced delays. Mail accumulated at processing centers but could not be delivered to routes still blocked by snow. First-class mail that normally delivered within 2 days took 4 or 5 days during the week following the storm. Package delivery services faced similar delays. The psychological impact on those who experienced extended vehicle confinement proved difficult to quantify but clearly existed. People who spent 20 to 30 hours in stopped vehicles, uncertain when conditions would improve, experiencing cold, hunger, and isolation, emerged from the experience with lasting effects. Some avoided highway travel for months afterward. Others developed anxiety about winter weather. These effects, though not measured in formal studies, appeared in anecdotal reports and media interviews. The storm's end brought a return to normal in stages. Each system, roads, rail, air, power, commerce, recovered at different rates. By Monday, December 2, the region functioned, though not yet normally. By Friday, December 6, most systems had returned to routine operations. The storm's acute phase lasted approximately 3 days. Its effects persisted for weeks. Total snowfall accumulation from the Thanksgiving 1985 storm varied by location. Southern Ohio counties along the Ohio River received 6 to 8 inches. Central Ohio, including Columbus, measured 10 to 12 inches. Northern Ohio saw 12 to 16 inches, with lake-enhanced areas receiving up to 18 inches. Indiana showed similar gradients, with southern regions receiving less than northern areas. Southeastern Michigan recorded 12 to 14 inches. The storm deposited measurable snow across approximately 100,000 square miles. Economic losses from the storm exceeded $1 billion in 1985 currency. This figure included lost productivity, damage to vehicles and infrastructure, increased energy costs, emergency response expenses, and lost retail revenue. Converting to later dollar values requires inflation adjustment, but the relative economic impact represented significant disruption. Transportation sector losses dominated the economic accounting. Commercial trucking lost approximately 3 days of operations across the affected region. Large trucking firms operated fleets of hundreds of vehicles. 3 days of stopped operations, with vehicles and drivers idle, created direct costs from lost revenue and continuing fixed costs. Smaller independent truckers faced similar proportional losses without the financial buffer larger firms possessed. Auto manufacturers lost production from parts shortages and plant closures. Detroit's major assembly plants missed 2 to 3 days of production. Each day of stopped production represented thousands of vehicles not manufactured. Assembly plants operated on thin margins where fixed costs continued regardless of output. The lost production affected quarterly financial results for major manufacturers. Airline industry losses included canceled flights, stranded aircraft, passenger compensation, and lost ticket revenue. Major carriers operating hubs in Cleveland, Detroit, and Indianapolis experienced hundreds of cancellations. Each cancellation represented lost revenue and continuing costs. Aircraft stranded outside their scheduled locations created scheduling problems that persisted for days. Airlines estimated losses in tens of millions of dollars. Retail sector losses came primarily from reduced Black Friday shopping activity. The day after Thanksgiving traditionally began the Christmas shopping season. In 1985, Black Friday represented a significant revenue day for retailers. The storm prevented shopping on Friday and reduced traffic through the weekend. Retail analysts estimated lost sales across the region in the hundreds of millions. Agricultural sector experienced limited direct impact. November represented a relatively quiet period for farming in the region. Harvest had completed. Winter preparation mostly finished. Livestock required care, and some farmers faced difficulty reaching animals during the storm. Losses occurred but remained small relative to other sectors. Energy sector costs included increased fuel consumption at power plants, overtime for utility crews, repairs to damaged infrastructure, and lost revenue from power outages. Utilities operated as regulated entities with costs eventually recovered through rates, but the immediate expenditures proved substantial. Government expenses included emergency services deployment, snow removal operations, National Guard activation, and highway repairs. State governments bore most costs, with some federal disaster assistance. Ohio, Indiana, and Michigan each spent tens of millions on storm response. Fatality counts varied by source and definition. Ohio reported 18 deaths directly attributed to the storm. Indiana reported 14. Michigan reported 12. These figures included carbon monoxide deaths, hypothermia, heart attacks during exertion, and traffic accidents. Indirect deaths, existing conditions worsened by cold exposure or lack of medical access, increased totals but remained harder to attribute directly to the storm. A reasonable estimate placed total storm-related deaths around 50 across the 3 states. Injuries requiring medical treatment numbered in the hundreds. Frostbite cases, primarily fingers and toes, represented the most common injury. Most cases resolved with treatment, but some required amputation of affected digits. Hypothermia cases requiring hospitalization numbered approximately 100. Fractures from falls on ice, vehicle accidents during initial snowfall, and injuries from physical exertion during snow clearing added to the total. Vehicle damage claims exceeded 10,000. Insurance companies processed claims through December and January. Common damage types included frozen engine blocks from extended idling, cracked radiators, depleted batteries, body damage from snow weight, and interior damage from survival efforts. Total insured losses exceeded $100 million. Infrastructure damage concentrated on power distribution systems. Broken power poles numbered approximately 500 across the 3 states. Downed power lines exceeded 1,000 incidents. Most repairs completed within 1 week, but some rural locations required extended repair time. Transmission system infrastructure experienced minimal damage. High-voltage towers withstood the snow load without failure. Bridge inspections following the storm revealed no significant structural damage. Bridges designed for snow and ice loading performed as intended. Some bridge deck surfaces required repair from snowplow damage, but structures remained sound. Highway pavement showed accelerated deterioration in spring 1986. The combination of wet snow, multiple freeze-thaw cycles during clearing operations, and heavy plow use created surface damage. State highway departments scheduled increased resurfacing for spring and summer. This represented deferred cost rather than immediate damage, but ultimately required expenditure. The storm's timing created educational disruption difficult to quantify economically. Students missed school days in varying amounts depending on district location and clearing progress. Some districts used snow days built into calendars. Others extended the school year into June. The educational impact, while not producing direct economic loss, represented a societal cost. Medical system stress, though not producing permanent damage, created temporary capacity problems. Hospitals operated at or near capacity during the weekend following Thanksgiving. Scheduled procedures were delayed. Emergency departments experienced overflow. The system absorbed this stress without collapse but operated at its limits. Comparative analysis placed the Thanksgiving 1985 storm among significant Ohio Valley winter events, but not at the extreme. The blizzard of 1978, which affected the same region in January, produced greater snowfall and more extensive disruption. The 1985 storm's impact came primarily from timing, occurring during peak travel period, before winter preparations completed, and on a major holiday. A similar meteorological event in mid-January would have caused less disruption despite potentially heavier snowfall. Storm recovery costs, the expenses of clearing, repair, and service restoration, exceeded $300 million across the 3 states. This figure included direct government expenditure, utility costs, private sector expenses, and insurance payouts. The economic disruption rippled through the fourth quarter of 1985, affecting GDP growth in the affected states. The Thanksgiving 1985 storm demonstrated that winter hazard stems not solely from snowfall amount or temperature, but from the temporal relationship between weather and social systems. A winter storm occurring when infrastructure stands ready, when travel volume remains low, when ground has frozen, and when expectations align with conditions produces manageable disruption. The same storm arriving at a moment of maximum vulnerability creates systemic failure. The storm arrived before infrastructure transitioned from autumn to winter operation. Snow removal equipment remained in storage. Salt stockpiles sat at low levels from the previous season. Personnel schedules had not shifted to winter readiness. Airports lacked sufficient de-icing capacity for the aircraft volume present. These gaps existed not from negligence but from reasonable management based on historical patterns. Late November typically preceded significant winter weather in the Ohio Valley. Policy discussions following the storm focused on readiness timing. Should municipalities maintain full winter readiness from November 1 rather than December 1? Cost-benefit analysis showed mixed results. The additional month of readiness prevented disruption from early storms, but imposed costs every year for events that occurred only occasionally. Most jurisdictions chose to maintain December 1 transitions, accepting the risk of occasional early-season storms. Some airports implemented expanded de-icing capacity and revised procedures for high-volume periods. The recognition that Thanksgiving week created unique vulnerability, combining maximum aircraft presence with potential winter weather, led to contingency planning specific to that week. These plans included pre-positioning additional de-icing equipment, arranging backup supplies, and developing protocols for rapid scale-up if weather threatened. Transportation companies revised scheduling practices for Thanksgiving week. Some trucking firms implemented earlier delivery schedules, completing Thanksgiving-related shipments by Tuesday rather than Wednesday. This reduced the number of trucks in transit during the peak vulnerability window. The practice imposed costs from overtime and compressed schedules but reduced risk. Weather forecasting improvements offered limited help. Forecasts in 1985 correctly predicted the storm's occurrence and general track. They underestimated accumulation and the speed at which travel would become impossible. Improvements in computer modeling and radar technology through subsequent decades enhanced accumulation forecasts, but predicting the exact hour when highways would become impassable remained difficult. Small variations in temperature, precipitation rate, or traffic volume created large differences in outcomes. The storm reinforced understanding that weather impact depends heavily on coincident human activity. An identical storm occurring on a random Tuesday in December would have created less disruption. Fewer people would have traveled. Expectations would have aligned with winter conditions. Infrastructure would have been positioned for winter operations. The Thanksgiving timing created the vulnerability. Public response to winter storm forecasts showed lasting effects. In subsequent years, winter storm warnings issued before Thanksgiving week generated higher rates of travel cancellation than warnings issued at other times. The 1985 experience created cultural memory that shaped behavior. People who experienced the storm, or knew someone who did, modified travel decisions based on that memory. This behavior change created a paradox. Heightened caution reduced vulnerability, but also potentially reduced the economic activity that Thanksgiving travel enabled. Family gatherings canceled due to weather forecasts represented disruption, even if the forecast proved less severe than predicted. The balance between appropriate caution and excessive response remained difficult to calibrate. Insurance industry response included refined risk models that incorporated temporal factors. Premium calculations for commercial vehicle insurance, business interruption coverage, and travel insurance began accounting for timing-dependent risks. Thanksgiving week, Christmas week, and other high-travel periods received different risk assessments than baseline periods. Emergency management planning incorporated multi-system failure scenarios. The 1985 storm showed that simultaneous disruption of highways, air, and rail eliminated all transportation alternatives. Previous planning often assumed that if one system failed, others could compensate. Post-1985 planning recognized that certain weather events could disable all systems simultaneously. This recognition led to stockpiling strategies, redundant communication systems, and distributed emergency resources. The question of acceptable vulnerability remained unresolved. Society could reduce winter weather risk by restricting travel during winter months, maintaining year-round winter readiness, or scheduling major holidays outside weather-vulnerable periods. None of these options proved practical. Instead, the implicit choice accepted some vulnerability as the cost of maintaining normal social and economic patterns. By mid-December 1985, the Ohio Valley had returned to routine operations. Highways cleared, schedules resumed. The storm became a historical event. Streets in Columbus, Cleveland, Indianapolis, and Detroit carried traffic normally. Airports processed flights on schedule. Rail freight moved without delay. The disruption ended. But the calendar remained unchanged. Thanksgiving would occur the fourth Thursday of November in 1986 and every subsequent year. Weather patterns would continue to produce occasional early-season winter storms. The alignment of these factors would occur again. The specific conditions of November 1985 represented one instance of a recurring vulnerability. The physical conditions that created the storm, Arctic air meeting Gulf moisture over the Ohio Valley, occurred as a consequence of atmospheric dynamics. These dynamics followed physical laws independent of human schedules. The social conditions, millions traveling simultaneously, infrastructure not ready, holiday timing, occurred as a consequence of human patterns. The collision of these two systems created the disruption. Awareness of this vulnerability did not eliminate it. Recognition that timing mattered, that early storms created disproportionate impact, that holidays concentrated risk. This knowledge informed planning but could not remove the fundamental dependency of modern society on uninterrupted transportation. The system operated with reduced margin during certain windows. This remained true after 1985 as before. The snow that fell November 27-28, 1985 melted by early December. Pavement dried. Vehicles moved freely. The physical evidence of the storm disappeared quickly. The systemic vulnerability that the storm revealed remained. Weather would continue arriving on its own schedule. Society would continue operating on its calendar. The risk lay in the moments when these schedules intersected unfavorably. Those moments would come again.